An immense, continuous, and unrelenting flood of free solar energy from our sun bombards the Earth every single second of every day. The targets of this extraction are photons, tiny, chaotic packets of light energy carrying that power across the vacuum of space. The physical challenge is that when these packets hit our planet, they normally just vibrate against atoms, lose their momentum, and dissipate uselessly as ambient heat. You cannot capture that kind of energy in a physical container. Catching it requires a trap engineered strictly at the atomic level. The foundational material chosen to build this trap is silicon. Silicon possesses a highly specific electrical threshold, known as a band gap. A band gap is the exact minimum amount of energy required to knock an electron loose from its atom. Silicon's threshold overlaps perfectly with the energy carried by sunlight. Pure silicon on its own is completely inert. Leave a raw slab of it out in the sun, and it does absolutely nothing. To turn it into an active energy pump, you have to physically manipulate its atomic architecture to force a specific, controlled outcome. Through doping, silicon is chemically altered into two layers. The top N-type layer gets phosphorus, creating a surplus of negative electrons. The bottom P-type layer gets boron, leaving positive holes. Pressed together, electrons drop into holes, creating a permanent electric field at the border. That field acts as a strict one-way gate. It establishes a boundary that prevents captured energy from ever returning to a state of rest. The extraction occurs the exact moment an incoming photon violently strikes the engineered silicon lattice. If the photon hits with enough kinetic energy, it forcefully ejects an electron completely out of its atomic bond. The second that electron breaks free, the permanent electric field catches it and shoves it down a designated one-way metallic pathway. As millions of photons continuously strike the panel, they force millions of electrons down this exact route. That continuous, directed flow of displaced particles is an electric current. A single atomic trap only generates a tiny fraction of a watt. To extract a meaningful payload, you have to link millions of these cells together into massive arrays. The initial electrical output from these arrays is direct current, or DC. This is a raw, single-direction flow of power. Modern household grids and appliances cannot run on raw DC power. They require alternating current, or AC, where the electrical flow constantly reverses direction. The system uses a device called an inverter to act as the translator. The inverter takes the raw DC power and electrically launders it into the AC format that the grid demands. Without that final conversion process, the captured cosmic energy would remain entirely isolated and useless to human infrastructure. There are physical limitations to this process. Under standard real-world conditions, a normal silicon panel is strictly capped at an efficiency of around 15 to 22%. This chart shows the broad solar light spectrum plotted against the narrow silicon absorption threshold. Because of the strict band gap, photons with too little energy pass through the cell undetected, and photons with too much energy lose the excess as pure heat, a physical limitation known as spectrum loss. To fight these losses, engineers physically alter the surface topography of the cells at a microscopic level, etching inverted pyramids into the silicon to trap bouncing light and force it deeper into the material. Extracting even 20% of a theoretically infinite energy source yields a staggering volume of usable power. This system executes the extraction with zero moving parts, zero exhaust, and no complex fuel supply chains. It operates silently and perpetually, integrating seamlessly into existing architecture and massive desert installations. The decentralized nature of this power grid allows electricity to feed silently back into civilization from millions of individual points. Mastering the physical mechanics of the photovoltaic effect bypasses our planetary limitations, finally allowing us to pull power directly from a star.